Hi everybody! Let's review what we have learned about classification with trees and random forest. Classification is a type of supervised learning. Supervised learning means that we know what kind of outcome we are looking for when we classify our data. In other words, we know that we have a class attribute that contains the labels that we want to assign to each one of our tuples in our data set. That is in contrast to unsupervised learning, specifically clustering, in which we don't know how the data fits together. Clustering is exploratory in that we ask our algorithms to look at the data and determine whether there are certain groupings of data that seem to belong together and that exhibit common qualities, common characteristics. From there, we can start to determine potential class attributes. In supervised learning, we already know the class attributes and we know their labels. Classification is really a two-step process. Of course, in step 0, we always want to make sure that our data set is appropriately pre-processed, and that means that we have removed any kinds of NAs, that is, we have developed a strategy of handling missing values. We have ensured that our class attribute is in fact categorical, and we have ensured that any implausible values have been handled either through imputation or through substitution, or maybe if they are at less than 10% of our data set, even have been removed. So once we are at that point that our data set is actually ready to be worked with, then we can start constructing our model. The first thing we do is we separate our data set into a training set and into a test set. That training set will have all class attribute assignations already in place so that we can start developing a model from it. That model typically comes in the form of one of the several trees that we're going to discuss in a moment. Once we have built our model, that is, once we have built our tree or our forest, then we can start using it. Before we do that, though, the first really important step is to estimate the accuracy of that model. We estimate the accuracy of our model by applying the model that we have developed on the basis of the training set to the test set, and then check the accuracy rate either as a percentage or in the form of a confusion matrix, which we'll be looking at in a moment. And if the accuracy is acceptable to us, either in terms of an R-squared value of more than 70% or of a sufficiently well-classified confusion matrix, then we can start applying our model to unknown objects. So at this point, we've worked with two different approaches. One was decision trees as a lazy learner, and one was the mathematical approach of the naive Bayes classification as an eager learner. In decision trees, our algorithm looks at each tuple and looks at the most likely assignment to a class label. Decision trees are compact, they're easy to implement, but remember that we can take it too far with our classification to the point where each tuple becomes its own leaf in a tree, and that's what's called overfitting. And to prevent overfitting, we have two options. We can either decide to tell our algorithm when to stop making branches in our tree. That's called pre-pruning. Or we can use several sets of test data and compare the trees that we're getting as our output and then decide to remove branches. That's called post-pruning. That way we are able to optimize our tree construction. Now, our naive Bayes classifier may look much easier to apply. All we're doing is we're taking the naive Bayes probability process, we're applying it to our data, and we get some pretty good results most of the time. However, one of the key assumptions of naive Bayes is that all attributes or all dimensions that we have in our data set are independent from one another, and practically that is not always true. For example, in healthcare data sets in which let's say symptoms such as fever and cough are often related, so that we are going to have to look at the presence and the dependencies among those with specific given diagnoses, or in which we have very frequently occurring comorbidities in terms of various cancers, the presence of pneumonia, the presence of diabetes, those kinds of things. So naive Bayes really has to be taken with a grain of salt. It is still one of the most popular classifiers. So now that we have built our model, we need to evaluate its accuracy and effectiveness. One of the tools that we can use to do so is our confusion matrix. Our confusion matrix shows us the relationship between reality, typically shown across, and the results from the application of our model, typically shown down. This gives us our true positives, that is the positives in a binary model that were identified correctly, our true negatives in a binary model, the negatives that were identified as actual negatives, and it shows us our type 1 and type 2 errors, namely our false negatives and our false positives. So for one of the previous examples that we've had in this course, where various age groups with various characteristics either do or don't buy a computer, we're seeing that in our sample confusion matrix, after the application of one of our tree algorithms, we have correctly identified out of 7,000 here, 6,954 who buy a computer, yes, in which the model has also correctly identified them as buying a computer, yes. And we have 46 who actually don't buy a computer identified as yes, they will buy a computer. We have 2,588 people correctly identified who will not buy a computer, and the model has identified them correctly. However, we also have 412 people who actually do buy a computer, identified as not buying a computer. So here we have our false negatives, here we have our false positives. So now that we have discussed the general process of classification and we have looked at the tools, especially our confusion matrix that we have to evaluate the accuracy of our classifications, let's take a look at the problematic of splitting the tree. For that, we're going to look at our three trees that we have discussed so far: our tree, our C tree, our conditional tree, and our R-part tree, which is our regression tree. Our problem that we are going to talk about is how do we optimize the tree. For that, we'll be taking a look at our sample data set, which is about a cricket game. Our class attribute is whether we play cricket, yes or no, based on an outlook, based on the temperature, the humidity, and whether it's windy or not. And our goal is going to be to find the smallest tree possible and to choose the attribute that produces the purest node. So the problem that we're going to look at is how can we split the decision tree in order to do just that. There are two strategies that we can pursue. One of them is called information gain, the other one is called the Gini index. Let's start with information gain. Information gain measures information in bits. That also means that the amount of bits should increase. That is, the value of the information that we're getting out of our tree construction should increase the further down to the leaf level we get in a tree. And because we are interested in the probability that a tuple is part of a branch of a tree, we're working with probability distributions, right? And if we do that, then we can work with the distribution's entropy because we are looking for the information that we need in order to predict the branch affiliation of a tuple. And our entropy formula reads like this. The entropy for our partition here is equal to minus our first option times the logarithm for that first option minus our second option times the logarithm for that option minus and so on depending on the options that we have. The important thing is that the logarithm here really helps us translate the information into bits. So this might have been a little abstract, so let's take a look at a concrete example and go back to our Cricut data set. We're first going to calculate the overall information gain. The overall information gain really is our class affiliation. So we're looking at our play attribute and we're looking at the labels and the label affiliation in our play attribute. And we're seeing here we have out of 14 tuples, we have 9 yeses, we have 5 nos. This means the information gain for 9 and 5, here is our entropy for 9 out of 14 and 5 out of 14. So 9 out of 14 and 5 out of 14. We're now going to apply the formula minus P1 times logarithm of P1 minus P2 times logarithm of P2 and so on. And what we're seeing here is minus 9 out of 14 logarithm 9 out of 14 minus 5 out of 14 times the logarithm for 5 out of 14. And that gives us, when we calculate that, an information gain of 0.940 bits. This means without even looking at a tree, we have an information gain of 0.940 bits. That's what's called the before split information. But we're not done yet because we need to analyze the information gain for each of our other attributes, outlook, temperature, humidity, and whether it's windy, in order to determine which one of these attributes has the highest information gain that allows us to optimally split our tree. So let's start by looking at our outlook attribute. Our outlook attribute has 3 levels here, sunny, overcast, and rainy. And we can determine by inspection that when it is sunny, our play attribute is yes in 2 cases, and it is no in 3 cases. All of that is 5, so 2 out of 5 and 3 out of 5. When it is overcast, our play attribute is constantly set to yes, and when it is rainy, we see 3 yeses and 2 nos. So this means we calculate the information for 2 out of 3, 4 out of 0, and 3 out of 2. We apply again our entropy formula that we've already seen here and that we have used here, but we're going to apply this to the class affiliation for each of our attribute settings. So for our outlook equals sunny, then we're seeing the attribute, the entropy for 2 out of 5 and 3 out of 5, and we're calculating minus 2 out of 5 times the logarithm 2 out of 5 minus 3 out of 5 the log times the log for 3 out of 5, and that gives us 0.971 bits. For overcast, since we are calculating the information for 4 and 0, that is typically undefined because we are really not getting any further information gain out of a attribute split that gives us all yeses. And we're going to do the exact calculation also for our outlook equaling rainy. Here we are calculating the information gain for 3 and 2 because we have 3 yeses and 2 nos. That also gives us 0.971 bits. So now that we have calculated the information value for each of our settings of the outlook attribute here, we can pull all that together and calculate the overall information value for the Outlook attribute. Here's how we do that. The information value for the Outlook attribute is the information for sunny plus the information for overcast plus the information for rainy. In order to do that, we're going to have to multiply each of our individual information values with the value of our play setting. So here we have 5 out of 14 for sunny, we have 4 out of 14 for overcast, and we have 5 out of 14 again for rainy, which gives us 5 out of 14 times 0.971 plus 4 out of 14 times 0 plus 5 out of 14 again here times 0.971, and that gives us an information value for the Outlook attribute of 0.693 bits. And now that we have the overall information value of our Outlook attribute, namely 0.693 bits, we can put that in relationship with the the before splitting information value that we've calculated at 0.94 bits, and that was just for the play attribute. Then we subtract our information value for the Outlook attribute from the information value for the overall play attribute, and that gives us 0.247 bits. So we're going to do the same calculation, not just for the Outlook attribute, but for all the temperatures, for all the humidities, and for all the windy settings. And then what we see is that the information gain, that is the result of subtracting the information value of our D1 attribute from the overall D attribute, which is the class affiliation. We're seeing the different values, and we're going to select the one that gives us the highest information gain, and that here is the Outlook attribute with 0.247 bits. Because in terms of information gain, bigger is better. So now that we have identified Outlook as giving us the highest information gain at the level D1, we're going to need to evaluate all of the other attributes in relation to the various Outlook settings, except for Outlook being overcast, because for Outlook being overcast, we remember we had 4 yeses in play, so that node is already pure and we're done. But we're not done for Outlook being sunny and for Outlook being rainy. At this point, we're going to have to look at temperature, windy, and humidity in relationship to that. So here is the scenario for Outlook being sunny. The information gain that we calculate based on this formula, going back through our entropy calculations as well. The information gain for temperature that we are calculating is 0.571 bits. The information gain for humidity that we have calculated is 0.971 bits, and the information gain for windy is 0.20 bits. This means, again, bigger is better. We're picking the split point with the highest information gain, here 0.971 bits, and that makes it humidity, for our Outlook being sunny. So for our tree shows Outlook being sunny, humidity is the next split point. This is different for Outlook rainy, where we calculate windy having the highest information gain by doing exactly the same math, and the numbers will of course look differently and identify gain for windy as the highest information gain, and we'll have the biggest number if we calculate it on the rainy branch. Our second method for determining the optimal split point or the optimal split attribute for a tree is called the Gini index. So here's how the Gini index functions. We calculate our Gini index for an entire data set, D, as 1 minus the sum of all possible split points times the probability of the split squared for each split. If we drill down a little bit, here's what this looks like. The Gini index for an attribute A on a data set D equals, here's the sum, if we split it into two subsets, because remember our initial assumption was binary splits, subset 1 over the entire data set times the Gini index for just the first subset, plus subset 2 over the entire data set times the Gini index for the subset number 2. And this also means that we need to compute the Gini indices for all of the possible split attributes. Our goal for the Gini index is to achieve the greatest reduction in impurity. So this means that we want to maximize our delta for the Gini of our attribute, which also means that the Gini of our attribute that we calculate here has to be really, really small so that the delta is maximized. Let's work through this with our sample data set about cricket. As with information gain, first we calculate our overall number, that is our overall Gini index for D, for our entire data set. So we know we have 14 tuples in play, 9 yeses and 5 nos. So we calculate our Gini index based on this formula here, which is 1 minus, and then 9 over 14 squared minus 5 over 14 squared. We come out with a Gini index for the entire data set of 0.459. And now we want to calculate the Gini index for each of the other attributes. So let's first look at the temperature attribute. We have the option here for the temperature attribute to either calculate no split and look at a split on nothing and everything, or a split on all three settings, hot, mild, cool, and nothing. But that's not a real split, so that doesn't make sense. We are not going to even look at these options. We can decide that we're going to split just on hot, on mild, or on cool, but that also leaves us with splits on hot and mild versus cool, hot and cool versus mild, and mild and cool versus hot. So we really want to compute a weighted sum of the impurity of each of the partitions, and then we're going to select the split with the smallest Gini index. Here's how this works on the D1 level. So let's assume that we partition our D into D1 mild and cool, that gives us 10 tuples here, and D2 hot, that gives us 4 tuples. So our Gini for temperature, mild and cool, is our D of 10 over 14 times the Gini index of D1 plus 4 over 14 times the Gini index of D2. Now we calculate the Gini indices. So it's 10 over 14 here, times the Gini index of D1, which is 7 over 10, those are the yeses here, squared, minus 3 over 10, which are the nos, plus 4 over 14, that's our D2, minus, and then the Gini index, 1 minus, 2 yeses out of those 4s, and 2 nos out of those 4s. Here are the 2 nos. Here are the 2 yeses. All that squared. When we do the math, we come out with 0.443 for temperature, mild, cool, and hot. We do that for the other splits as well. If we calculate the same thing for hot and cool versus mild split, our index will be 0.458. If we calculate this for a hot mild versus cool split, we receive 0.45 as the result. So our split temperature for mild and cool versus high, or versus hot, has the lowest Gini index. We do exactly the same math for all the other attributes, for humidity and for windy. And in humidity, again, we look at high yes, high no, 3 and 4, normal yes and normal no, 6 and 1. That's this here. and we look at windy, false, yes, false, no, true, yes, and true, no with these values. And we do exactly the same math. We do here 7 over 14, 7 highs, 7 normals over 14, and here is our math inside of our highs and our normals. And we do the same thing for windy, false. Here's the 6 and 2, and true, 3 and 3, and of course here's the overall, and our result is 0.5. So now our results are 0.443 for temperature mild cool, 0.458 for temperature hot cool, and 0.45 for temperature hot mild. We also have Gini index for humidity of 0.7143 and for windy of 0.5. So how do we determine the optimal split point? Well, remember that we're looking for the smallest overall impurity, because we're going to maximize our purity and to minimize our impurity. Our overall Gini for the data set was 0.459, so what we want is we want a really large number here to minimize this. This also means if we look at our temp mild cool split versus hot, we subtract the 0.443 that we've calculated over here. We are then going to subtract the 0.458 that we have calculated over here, and in another attempt is 0.45. And we find here the impurity is at 0.016. Here is the smallest impurity. That's really promising already. But then let's take a look at windy, because for windy we had our Gini set calculated to 0.5, and for humidity we had it calculated at 0.7143. So what that means is if we want to have the smallest overall impurity, that is the greatest purity, then we will subtract the largest number here, and that means that the optimal, the smallest impurity that we can achieve is minus 0.2553, which we get by subtracting the impurity that we have calculated for humidity and subtract that from the impurity from the Gini index for the overall data set. So the optimal split point will be humidity. So now the question is, can one tree ever be enough? The answer to that is, of course, no. This is where in the 1990s, scientists have started experimenting with combining different classifiers, trees, other classifiers, into a combined model in which the different models or different experts will then vote for the classifiers whose results match the closest, and those would then become a combined and aggregated model to more efficiently predict the class labels for unseen data. That would ideally improve the predictive performance. And since we're combining a number of classifiers, that would also possibly be easy to implement. The problem with that would be that the combined classifier wouldn't be as transparent, and also we can't really represent this in any kind of compact fashion. Now, this started, as I said, in the mid-90s with an effort at bagging and bootstrapping, and it culminated kind of from 2000 onward, 2001 onward, in the first idea about random forests. Now, random forests, or the random forest algorithm in general, really has an advantage over bagging and bootstrapping in that random forest takes from the same training set a number of subsets, however many we tell it to, and it samples these with replacement, so that each of the subsets, each one of the multiple training sets that we're producing from one overall training set is always only slightly different. And the difference is based on randomization, on random sampling with replacement. Then what we're going to do is we're learning the tree, but not just one tree. We're learning a tree from each one of these randomly generated sub-training sets that are all slightly different. This also means that each tree that we're learning is also going to be slightly different. And then we're going to use the data sets that are not included in any of the random little training sets. And we're going to predict the class membership of each of those random data points that were not included in the random data set and the random training set. And then we're going to compare the accuracy of the predictions. And as we compare the accuracy of the predictions of each tree that we've built on each of the randomly sampled with replacement little sub-training sets, then we will come out with an optimal model. We take the majority vote for the outcomes of the class membership predictions. That way we can greatly improve the accuracy of our predictions, because if many trees that are all built on slightly different training data sets and that are in themselves slightly different trees give us similar or even the same predictions, then our model drastically improves and we reduce our error rate. So let's assume that we have 25 base classifiers, 25 trees. If each classifier has an error rate of 0.35, if we assume that all these little trees are independent from one another, then we can say that the overall error rate for our 25 base classifiers is going to be reduced from 0.35 to 0.06. And this huge improvement is why random forest is so incredibly popular. At this point, please go back into Blackboard and review the sample files in R and in Python about our trees and about random forest. Each one of these files is extensively commented to help you understand what each line of code does and how to interpret the output you will be seeing. If you have any questions, please don't be shy and ask, or post any questions into the questions forum as well, and we will be sure to answer them as a team together, and of course I will review them as well. Thank you.